So cosine is our x, sine is our y. What's the radius on our unit circle? 1. Always, right? All the way around, the radius of the unit circle is 1. So what we did was we are about to derive the Pythagorean identity that all of the others come from. This means cosine squared plus sine squared equals 1, our hypotenuse. That is the only thing that you have to memorize of everything that we're going to do today. Because everything else we can get from it. We can get every other iteration of the Pythagorean identities from this first one. Cosine squared plus sine squared equals 1. And of course, the order doesn't matter when you're adding. So you could remember it as sine squared plus cosine squared equals 1, and that's the same. Okay? Comes right from the unit circle. Now, this is an identity, which means it is always true, no matter what value of x you are using. No matter what value of x. And again, this is what you're memorizing. And then you just have to know how to use it. This is always true, but cosine plus sine equals 1 is not always true. That's only true a couple places. Cosine squared plus sine squared equals 1 is true everywhere. Any value of x. Any legal algebra that we do to this is also an identity, is also true no matter what. And I say legal algebra on purpose because every once in a while we use some legal algebra. But let's do a couple of things to this to get this into forms that we use most often. So cosine squared plus sine squared equals 1 is a form that we use very often. Another form that we use, a little bit of addition and subtraction. If we subtract cosine squared to the other side of the equation, that is a form that is very useful. So my cosines cancel, sine squared equals 1 minus cosine squared. That is a form that's very useful. If we have sine squared and we would rather be working with cosine squared, this is what we would use. And if we have a sine squared, we could put 1 minus cosine squared into that equation. Similarly, we can subtract sine squared from both sides of the equation. And we get cosine squared equals 1 minus sine squared. So there, anywhere we have a cosine squared, if we'd rather work with sines, we can put in 1 minus sine squared. Again, this only works for squares. Only works if you have sine squared and cosine squared involved. And we'll do some examples today and some examples on Monday. And this work right here, where you're subtracting to the other side of the equation, that's something that if I need to, I do like kind of off to the side in the middle of a problem. So I'm like, ooh, I don't remember. Let me just go ahead and do that off to the side and then substitute it. The other two identities come from that first one. So it looks like you have a lot to memorize. If you're trying to memorize everything, we're kind of boxing up on these notes. But all of it comes from that first one. So our first up there, let's get 1 plus cotangent squared equals cosecant squared out of this. So, I forgot to talk about this. I only think 1 or 2 people have asked, why is the squared there? So the square root is there, the square root is in the middle, because if we put it out here, it would look like cotangent of x squared, and you would need parentheses around the whole thing to show it's the whole function squared. So the squared in the middle there shows that you're squaring the whole function. If it was just x squared, it would be out here. That's the same. You could also write it as cotangent of x squared. Those are the same. Whole thing squared is what we're doing. Okay. So let's get cotangent and cosecant out of this. So to get 1 plus cotangent squared equals cosecant squared, instead of subtracting, which is what we did to get other identities, I'm going to divide. I'm going to divide everything by sine squared. And the reason I remember that is because I know I want cosecant. And if I know I want cosecant, then I want 1 over sine. So cosine squared over sine squared is cotangent squared. Sine squared over sine squared is 1. 1 over sine squared is cosecant squared. And cotangent squared plus 1 is the same as 1 plus cotangent squared. Those are the same. Again, any legal algebra you do to this is also an identity. So if you wanted what cotangent squared is equal to, you could subtract the 1 over. We're never taking the square root of both sides here, though. This doesn't work for singlets. It only works for squares. What do you think I'm going to divide by to get tangent and secant squared? Yeah, cosine. So we're going to divide everything by cosine squared. Cosine squared over cosine squared? 1. Sine squared over cosine squared? Tangent squared. 1 over cosine squared is secant squared. When I am first working on this unit, after I haven't worked on it for a while, I don't have these memorized fresh in my brain. I know cosine squared plus sine squared equals 1, and I can get all of these other iterations. And so if I find I need cosecant, then I just divide everything by sine, because I know if I want cosecant, I want sine on the bottom. If I know I want secant, then I know I want cosine on the bottom, so I'm going to divide everything by cosine. This is all working, and again, you don't have to have it memorized as long as you know how to get to it. And all you're doing is basically little one-step equations to get to it. All right, flip over and let's use it. Again, you don't have to memorize it as long as you can get to it. Questions for you're using? This is really just going to do 2 examples. I'm going to let you do some examples. Then Monday I'll do more examples and do more. All right. Sine squared minus sine equals cosine squared. So when I'm deciding what to set clearly, we're going to use the Pythagorean identity because this is on the Pythagorean identity note. I need to figure out where to substitute in. So when I'm looking at this, I know I can substitute in for sine squared. I know I can substitute in for cosine squared. The only thing I can't change is sine. The only thing I could change sine to is 1 over cosecant. Anyone interested in that? I didn't think so. Let's not introduce fractions if we don't have to. So if my singlet is sine, that tells me that I want to put everything in my equation in terms of sine, if I can. So I want to get rid of my cosine squared. So you kind of go with that singlet. If I had sine squareds and cosine squareds, it wouldn't matter. If that was my whole problem, you could go either direction with it. You could could go sine squares or you could go cosine squares. But since I have that sign there, that's going to derive what I need to do. So I need to substitute in for cosine squared. So flip back on your pretty notes. And let's figure out what I can substitute in for cosine squared. Cosine squared is the same as 1 minus sine squared. So that's what I'm going to plug in instead of cosine squared. Everything else in the equation is going to stay the same. And if off to the side you want to do that math for yourself, you're saying, she's only saying I have to memorize that. This is how that would look if you're on a test, in the middle of a test, and you want to make sure. Cosine squared plus sine squared equals 1. To get cosine squared by itself, I need to subtract sine squared. So cosine squared is equal to, I know this just totally ran into the pretty little border. Cosine squared is equal to 1 minus sine squared. That's all you have to do off to the side if you don't want to memorize that. All right? And now we need to solve. And since I have squares involved, I know I'm going to need to factor. So I'm going to get everything onto the same side of my equation. So I'm going to add over my sine squared to its like term. And subtract my 1. So sine squared plus sine squared is 2 sine squared minus sine minus 1 equals 0. And now this looks like, well, actually one step ago, this could have been a problem that I gave you last week. Right? The only thing new today is doing that substitution to get all one function, all sines, or all cosines, or all cotangents. Now you can do U substitution if that helps your brain, which it does mine. So let's let U equal sine of theta. Kind of like you let your singlet, you're not your squared, your singlet drive where your problem's going. We always let our U be that middle term. So this is 2U squared minus U minus 1. Two numbers that multiply at -2 and add to -1 are 2U, -2 and 1. And you can substitute back in whenever you're ready. So you can substitute back in the parentheses, you can set your U equal to, you can solve and substitute back in. Whichever you do, you're going to end up with sine of theta equals -1/2 and sine of theta equals 1.
The only thing I did different with that is I got +/-1 because like I couldn't use square root square root.
Where did you have it U squared?
Oh wait, I wrote that.
No problem. All right, so where is sine -1/2? Yep. Quadrants 3 and 4, so 7 pi over 6 and 11 pi over 6. Remember, we need to write those little equations so we get all the rotations around the unit circle. If it helps you to figure out whether you need to do plus pi k or plus 2 pi k, do your little diagram. 7 pi over 6 and 11 pi over 6 are so they don't make a straight line. So we're going to write our two solutions separately. We're going to do theta equals 7 pi over 6 plus 2 pi k. And theta equals 11 pi over 6 plus 2 pi k. And then we're not going to forget that we also have to solve for where sine equals 1. And sine equals 1 on pi over 2. And pi over 2 is the only place, so there's no decision to be made whether we need plus pi or plus 2 pi k. So pi over 2 plus 2 pi k. And remember, the plus 2 pi k just gives you those rotations that give you angles that are bigger or smaller than your unit circle. Questions about that first example? There's a lot going on, but only the first step was new. All right, one more example for you today. Cotangent, and here A is our variable, cotangent plus 3 equals 3 cosecant. Again, cosecant, we could turn into 1 over sine, but let's not introduce fractions if we don't have to. So let's go back and look at cotangent squared and see what we can do with that. So the identity that puts cotangent squared and cosecant squared together is right here. 1 plus cotangent squared equals cosecant squared. We're going to leave our singlet alone and substitute in for the square. Leave the singlet alone, substitute in for the square. So what can I put in for cotangent squared? Well, what math do I need to do over there? Yeah.
Is cosecant squared minus 1?
Yes. Subtract 1 from both sides on that identity. And that's what you can substitute in. So cotangent squared is the same as cosecant squared minus 1. And then the rest of our problem is going to stay the same. Plus 3 equals 3 cosecant of A. Once you do that substitution, you should only have one trig thing going on. One trig expression. If you look across and you still had a cotangent somewhere, it's not going to work. If you look across and you had a sine somewhere, something, it's not going to work for you. Okay, let's combine our like terms. And then move over that 3 cosecant of A so that we can factor our trinomial. That's going to be our middle term of our trinomial. So I end up with cosecant squared minus 3 cosecant plus 2. You can factor just as that sits if you're comfortable, or you can do U substitution. You can always do U substitution. So this would just be U squared minus 3U plus 2. Which is nice. That's a nice one to factor. Go directly to your shortcut. You don't even have to split the middle on this one. Two numbers that multiply to 2 and add to negative 3. Negative 2 and negative 1. And you should feel good about that, thinking about cosecant, since cosecant is a reciprocal of sine. So this means that U equals 2 and U equals 1. rather work with sines and cosecant, I would as well. If cosecant is 2, then sine is 1/2. If cosecant is 1, then sine is 1. So on your unit circle, sine 1/2 at pi over 6 and 5 pi over 6. And those are not pi apart. Since they're not pi apart, we do plus 2 pi k to give our equation for all solutions. Sine is 1, we just did that in the last problem.